Okay, what does it mean for two things to be inverses? Well, if I have 2 to the third equals 8, I can rewrite that as an equivalent logarithmic term. Why? Because they're inverses. The base would just stay the same. So what's the base of our exponential here? Well, it's a base of 2. So I could rewrite it as a log base 2. Except for what I need to think of as my other two numbers, my 3 and my 8, treat those as like an x and a y. Well, if we're talking about a log being an inverse, that means I would need to, remember with inverses we swap our x and our y. So, well, on the exponential, the 3 is with the 2. If we swap our x and our y, that means the 8. When I'm looking at the log with the same base, will be with the 2 instead of the 3. That means the 3 will actually move to being on its own on the other side. So our equivalent statement as a log using inverses would be that the log base 2 is of the 8 this time. The 3 is now on the other side by itself because we swapped the x's and the y's, but we kept the base the same because they are inverses. So let's try this out. Let's look at A. On A, we have 2 to the 5th equals 32, which we know is a true statement. We want to write the same statement, but we want to do it in logarithmic form. And what that means I need to do is I need to use my properties of inverses. So if we have, like we do in this one, an exponential that's base is 2, it's going to turn into, when we use our inverses, a logarithm, base 2. But, because I'm using rules for inverses, I need to swap my x and my y, which are my 5 and my 32. So if I swap the sides on my 5 and my 32, my x and y, it'll be log base 2 of 32 equals 5. That's it. Let's look at B. On B, I have an exponential base 2/3. So when I use, again, my properties of my inverses, I'm going to turn this into a log base. It'll look a little funny. Log base 2/3, that's, remember, a subscript. But then again, just like the last one, I have to, because they're inverses, swap the x and the y, the other two numbers. The -3 and the 27 over 8. So the 27 over 8 is going to be on the left-hand side now, equals the -3 will be on the right. And that's it. So we'll have log base 2/3 equal of 27 over 8 equals -3. Last one, let's look at C. So let's see, what do we have here? On C, we have an exponential base E. So what's the log that matches up with that would be the log base E? Well, we don't use log base E. We actually use special one. We use ln, the natural log. Just like before, though, we have to take the x and the y, the other two numbers, and swap because they're inverses. So that means that natural log of 1 will equal 0, swapping the x and the y, and we're done. Now let's do the reverse. We're going to take a logarithm and write it as an exponential. We're still going to do the same thing. We're going to use our rules for inverses, though. So if we have, like we do on this first one, a log base 5, we have a log base 5, we're going to rewrite it as an exponential base 5. But just like before, we're still dealing with inverses. We have to swap the x and the y, the other two numbers. Well, remember this is an exponential function, though. So when we move the 1 over to the left-hand side, it's going to be the exponent on that base of 5. And then the 5 will be on the right-hand side by itself now. What's cool about this direction with exponents is you can make sure that your answers are actually making sense. Well, does 5 to the first power equal 5? Yes, it does. So this is exactly right. This is the statement that it turns into, and it is a true statement. So this is what we've got. The statement 5 to the first power equals 5. Now, let's look at the next one. On B, we have a log base. Let's see, we have a log base 4. So when we use our properties of inverses to rewrite this in exponential form, it'll still be a base 4. The only difference is we're going to be swapping out our x and our y, the other two numbers. We'll be swapping those out. So when the -3 moves over to the left-hand side, we're now dealing with an exponent, so it'll become our exponent on our base here of 4. So it'll become a -3 here. Equals, now the 1 over 64 will be on the right-hand side by itself. Now let's make sure that this makes sense. We've got 4 to the -3rd equals 164. What does a negative exponent do? Remember, it drops itself to the bottom of n fraction, so this would become 1 over 4 to the 3rd. Well, we know that 4 to the 3rd is 64, so yes, this is a true statement, and that's what we were looking for. The exponential form is saying 4 to the -3rd equals 1 over 64, and we do know that that is definitely true. Let's look at C. In C, we have log base 3. So this would turn into, when rewritten, an exponential base 3. The only difference is we again have to use our rules of inverses and swap our x and our y, which means the exponent on my 3 is actually going to be, the 2/3 is going to move over there. Will equal, the cube root of 9 will move to the other side. And there's our equivalent statement. Now, to make sure that this makes sense, which it does, remember the 3 on the bottom tells you what kind of root you have, which is a cube root. You'll have a cube root of what? Well, 3 squared, which is 9. So, does this make sense? Absolutely. So, our final answer is that 3 raised to the 2/3 equals the cube root of 9. That's the exponential form of this equation. One last problem. On this last one, we have a log, an LOG. We don't see a base, though. Remember, if we don't see a base on an LOG log, it's a hidden base of 10. You still have to do what we've done before, which is take your other two numbers, which kind of treat those as your x and y, and swap those because they're inverses. Now we're dealing with the inverse. So our exponent on the 10 should be 2, and that should equal 100. Well, 10 squared is 10 times 10, which is 100. So yes, this is definitely a true statement, and that's my exponential form I was looking for, that 10 squared equals 100.